Well, welcome again. This will be the final lecture. So just to recall what we did. So in the first part, we sort of explored the physics side of this thing, the genesis of the problem, so to speak. And on the second lecture, we sort of try to define some things to be able to state the main result. We saw also some examples, and I showed more or less how the proof would go if you wanted to specify the proof only to Poisson summation. Okay. So now the goal is to sort of reach the result and state it, and to give a proof of the result in the best way I can. But I'll have to skip a bunch of things, otherwise we'll be here too long. And then in the end, I will try to give some applications. Okay. Okay. So let's start with. So the main object here will be almost periodic functions. So let's start with that. And there'll be two types of it. The first type would be on the real line, and the second one would be holomorphic almost periodic functions. So let's start with this with a simple type. So definition. So we say that a function f, and I would denote like this, is almost periodic on the real line. So that would be what? That would be a function from the real line to the complex plane. If first f is continuous, and for every epsilon positive, there is a set tau of epsilon translations, and this set is relatively dense. So there exists a set tau of, it's called a set of epsilon translations. Which is relatively dense. And I will say what is that in a moment, such that the following holds. You take the sup for every t in your set tau. So what you can rewrite this in a convenient way. This would be the sup norm of, if you translate your function by t, and you take the sup norm of your translation by t minus f. Let me write it like that. And I write the sup norm like this. This would be less or equal than epsilon. Okay? Relatively dense. Let me open a box here. Means that there is L positive, such that for every x real, x plus L intersects your set. Okay? So there will be a length where if you run that length over the real line, you always see a point of your set tau. That means relatively dense. Okay? So what you have, one picture in your mind is that you have a set of points, and there is a minimal spacing between them. They can't be too far apart, otherwise they can't be arbitrarily far apart, otherwise such an L wouldn't exist. Okay? So there will be some point, some length that you always see the next point, and if you translate your function by those translations, it gets very close to the original function by epsilon. Okay? So one exercise you can show that your set of epsilon translations is actually closed and has no empty interior actually. Okay? So that's one exercise. Okay, and there is a very nice criteria. So this was first defined by Bohr, the brother of the famous physicist, and with the idea to I think it was specially connected in those days. It was specially connected with dynamical systems. Nowadays, these functions appear in several other fields of mathematics. But he had in mind these kind of functions, for instance. So an example, it's a trig polynomial. And for me, a trig polynomial is anything like this. Where the theta j's is just some collection of real numbers, okay? And cj's are just some complex coefficients. Okay, that's a trigonometric polynomial. Okay, and so this function should be almost periodic. Okay, that's what he had in mind, and it actually is. So you can show that Q is almost periodic. Okay? But it's not so straightforward because, well, one guy is, obviously, it is periodic. But once you add the second guy, how you can come up with the set tau? Okay? There's a nice criteria. It's Bochner's criteria. What's Bochner's criterion? Suppose you take f a continuous function. Okay, first I have to say something. So whenever I look at the continuous function on a real line, I look at it with the sup norm. So I have an induced topology with that norm, and that will be a Banach space, and so that's how I will view this set. Okay. And so Bochner's criteria is let f be continuous, then f is almost periodic if and only if you look at this set here, the set of translations of f, and you can ask how is this set placed inside this one, and it's if and only if the set is pre-compact. Pre-compact is just to say that the closure is compact. Okay? That means that if you take any sequence of translations of f, there will be a subsequence of translations which converges uniformly to some function. That's Bochner's criteria. Okay? To show this is not straightforward. You need some tricks. Okay? It's not obvious. Okay? But that solves the problem of showing that this is almost periodic. Okay? Why? Because if one function is almost periodic, if and only if this is pre-compact. And if another function is almost periodic, again, but then you consider the sum. Okay? Well, for the first one, so if you take a sequence of translations, for the first one, there will be a subsequence that converges. And from that subsequence, you take another one for the second one. And so you can come up with a subsequence where both converges uniformly. Therefore, the sum converges, satisfies this criteria. Therefore, the sum is almost periodic. So you have to use this to prove that result. You can also use the result of Kronecker, which is an old result, to prove it directly, but then you have to prove Kronecker's result, which is a pain, let's say. You can prove Kronecker's result using almost periodicity, so it's one of the applications people do. But that you would need Bochner's criteria. Okay, so it's very useful to show that. So from this, you deduce that the almost periodic functions you can add up, you can multiply by scalar, so it's an algebra. Okay. There is one slightly problem. Suppose you have an almost periodic function on the real line which is never 0. Is 1 over f almost periodic? That's not always the case. Okay, it will be the case when we consider almost periodic functions but holomorphic functions. Then that will be the case. Okay, so when you go to the holomorphic theory, it's a bit better. And also from this, you deduce that, well, what I just said. There's another very nice result of Bochner. Bochner's approximation theorem. What he's going to say is going to say the following. So let f be almost periodic. One thing you have to notice. Suppose that f, you have a sequence of f's, fn, which is converging uniformly to some other function f. And then you know that each fn is almost periodic. Then you deduce that f is almost periodic. Okay. So it's closed by uniform convergence. Okay. Okay. So let f be a most periodic function on the real line. Then for every epsilon positive, there is a trigonometric polynomial p such that okay. So any trigonometric polynomial you can uniformly approximate by a trig polynomial. Any almost periodic function you can approximate by a trig polynomial. So what you say is that if you look at the almost periodic functions and you take the closure with the soup topology, let's write it like that, what you get, trig polynomials, what you get is almost periodic functions. Okay. So these are very old results from the 1910s, 1920s. Okay. And there is a very nice almost periodic functions have Fourier series. Okay, so let me, yes. So I will use this notation. E of f of lambda equals the limit when t goes to infinity minus tt of f of x e minus 2 pi I lambda x dx. Okay. You take in an average, so you take integrating from minus t to t 1 over 2t, sending capital T to infinity, and you take in an average. So you're sort of trying to compute the Fourier coefficient, and I call this Fourier coefficient sort of an average of f at the point lambda. Lambda here will be a real number. Okay? So if f was periodic, what you can show is that if lambda is an integer, this thing, I mean, this always converges. If lambda is an integer, it's not guaranteed if it's going to be 0 or not, but if it's not an integer, it's 0. Okay, if f is one periodic. And so there is a theorem, which is, I'm going to say, I'm going to write it like that, which says that this makes sense in some way. Okay, so how is this going to make sense? This is what I told you. So let me write it like theorem. Let f almost periodic, then 1, what you have, this always exists. So notice something. So if f is almost periodic, then if you multiply by exponential, it's also almost periodic by Bochner's criteria, or it's an algebra. So what you have to do is just to show that the average at 0 always exists for any almost periodic function. That would show that this always exists. Okay? And then you have to use the definition. Okay? 2, if you define the spectrum of f as the support the lambdas real, such that E of f is not 0, the lambdas that you get something non-zero, you can show that this is countable. Lambda 1, lambda 2, lambda 3, lambda 4, and so on. It's countable. And 3 is, if the spectrum of f is empty, f is 0. And finally, for if you do E, so again, norm of f is squared is almost periodic because it's just f times f bar conjugate. And I said that this converges if I do this. Okay? Let me write it like that. So if you do that, what do you get? You get Planck error. Okay? So remember, in the last class I said that the function is locally summable. Let me write it right here. In the last class I said a function a, I said locally summable if the support of the function is countable and local sums are well defined. Okay? So how do you sum over all the reals in an interval? Well, the support is countable. So you take any enumeration, you do the summation. If it's finite, it's independent of the enumeration. Okay, so that's what I'm saying. Okay, so the item 4 is saying that this function here, that for a lambda associates the square, it's not only locally summable, it's globally summable. Okay, because this is finite by the other item. Okay. And there is even 5 which would say that if this sum here is finite, then let me use the other color. Then actually you have the representation. You have Fourier representation. This is equal to this sum. And now this sum makes sense because these are exponential. I have norm 1. And I'm summating over all the real numbers. Okay? So in a way, we can say this. Okay? Again, more than 100 years old, this thing. Okay. so now what I'm really going to need is not the notion of almost periodic functions on the real line, but actually in the complex plane. Okay. For instance, this result here might seem weird. Né? How can I show that this thing is countable? Okay, what you do, take a trig polynomial, Pn, that such that the infinite norm is less or equal to 1 over n, for instance. Okay? Then you have to show that, and then, so it's a trig polynomial. It's a finite sum of some thetas. You have a Pn, so you have some thetas, and you take the union of all these thetas for all the n's. Okay? Then you show that the support, the spectra, has to be contained in this union. But it's a enumerable union of finite sets, so it's enumerable. Okay? That's how you show it. Okay. So, but now we want almost periodic functions. In the upper half plane, okay, especially. But in principle, we can define it for any strip. So you can also do it for strips. And for me, a strip would be something like, here you have the complex plane, and you take a horizontal strip. Okay? And that would be a strip. Say a strip S. Okay? And you can make a theory of almost periodic function on strips. Okay? But I will stick with C+. Okay, so we will say that F belongs to almost periodic in C+. If the same thing happens as before, so F is holomorphic. So we change continuity by being analytic. And for every epsilon positive, and for every substrip contained in this strip, then that is for every alpha and beta positive with 0 less than alpha less than beta, there is a set tau relatively dense, such that if you take the sup for z in this strip, which would mean if you take the sup in that strip, so this would be alpha and this would be beta. Okay, so most periodic in C+ would be you take any substrip and you take epsilon. Once you fix that, there will be a set of epsilon translations. So tau might depend on epsilon, but also on alpha and beta. Okay, that's almost periodic in C+. It's similarly, you could just fix a strip S and then consider the same thing, but now you take any substrip. Okay. And essentially the same results as before hold true. Almost periodic in C+ will contain trigonometric polynomials in the same way as defined before. Okay, but now you consider x just as a variable, complex variable, say z. Okay. You have to define what is the average. The average here is going to be the limit when t goes to infinity, 1 over 2t minus t plus iy, t plus iy, and then you do f of z minus 2 pi I lambda z dz. Okay, so you take a line here and you integrate and you do an average. Okay. Now the right hand side has a y, the left hand side doesn't. So what I'm saying is that you can show that this exists and is independent in the of y positive. Essentially by Cauchy's formula, yes. You integrate and then the upper part not going to matter. Oh, I forgot a condition. So f is a most periodic. Let me see. Oh, no, it's correct. So there is a nice lemma which says that so a function is almost periodic in C+, if and only if it's bounded on strips. So for every strip, it's bounded. Of course, it has to be bounded because you have this. And so the sup of the function will be bounded by a sup in some bounded rectangle here. Okay, so it's going to be bounded on strips, strictly contained in C+, in the upper half plane. So f is going to be a holomorphic, almost periodic function in C+, if and only if you can show this. If f is bounded on strips, and there is one line such that f is almost periodic as a real function, I mean, the sense before, in that particular line. So from one line, you can extrapolate to everything, okay? As long as bounded on strips. Okay, that's a nice, and then from this result, you can sort of recover everything. You can, once you have this, you can recover this result as well, that is countable. And then also what you have is this, let me see. Yes, what you have is also this. So if you look at this function as a real function of this variable, take the square, take the average at 0, that's going to be exactly equal to that. Okay? This for every y positive. Okay? This is just a statement that if f is almost periodic in C+, it means that for every line, f is almost periodic, and then you just apply the previous result, rearrange, and you get this. Okay. There's a slight difference here because I'm integrating over z. So if you really look at this integral, there will be 2 pi I y, 2 pi y coming out, lambda, 2 pi y lambda coming out. That's where this extra factor shows up. Okay. Okay, so I think this is essentially what I need. You also have the approximation theorem, which would be exactly like this, but restricted to strips. For every strip, you fix a horizontal strip. In that horizontal strip, you can approximate your f by a trig polynomial as much as you like, as close as you like. Okay. Okay. So now, now I need representation results. This is the second part. So in a way, this is all the prerequisites of the theory I need for the dual part of the result I want to present. Now I want to show the, say, so that would be the Fourier part. Now I want a frequency part. So now I want the space part of it. So let me say Poisson representation. Let me see if I'm going the right direction. Yes, okay. So I need two definitions, one definition. So first definition. So suppose I get a function f c plus, let's see, holomorphic. So we say f is of bounded type, and I write it like this. That means bounded type if there is two functions, say u and v, holomorphic and bounded, such that f is u divided by v. So a function is bounded if it's bounded, but bounded type means it's a quotient of two bounded functions. So it's bounded type. Okay. So what you can show is that if that exists, if f is of bounded type, then you can define this, which is called usually the mean type. And by the way, this is the way I'm presenting. This is mostly due to, the way I'm phrasing it. The Bruns and Nevalina. Okay, from the 40s, I think, 50s and 60s. So what's the mean type is the Lim soup when y goes to infinity of the log of the moduli of iy divided by y. Okay, so you can show that this number is always finite. Okay, it's not infinity. It could be minus infinity, but it's finite. Okay, mean type. Okay, now I need to state the result, and then we're almost ready. So proposition let f be of bounded be holomorphic and let g equals the exponential of f. Okay? Then the following are equivalent. One, there is a measure, mu, on the line. Let's say mu real valued. On the line, and the if you integrate its total variation against t squared is finite, such that and if you look at this and you remember the last talk, you will see that there is already a connection okay. So the following equivalent, condition 1, there is a real valued measure on the line which its total variation integrates 1 over t squared, such that this representation holds. 2, what's equivalent to that? G is bounded type, and its mean type is 0. Okay. So that is the connection we needed. In the last class, remember that f there was just I cosine of pi z divided by sine of pi z. Or we recall, like for Poisson summation, remember that f was I cosine of pi z sine of pi z. Okay? And that's a function such that has this and this holds. Okay, when g is e to the f. Okay. And that was the measure that we wanted. That was mu coming from the Poisson summation. This is sum of deltas over the integers with unit masses. Okay. And that was the key thing, because that would show that if we consider that function which was an exponential on one side, exponential on the other, and apply that to the fs pair that we defined, you would get an identity like that. And from that, you could recover everything. Okay? So sort of this is the key identity that connects the physical part and the frequency part. Okay? So for that, you have to, the proof here, and I'm going to show this, requires Nevalina factorization. For G. Okay? So Nevalina's factorization sort of states a function G is in bounded type if and only if it has a particular kind of Hadamard factorization with the Blechy product plus exponential of something else. The Blechy product would deal with the zeros. Well, G here doesn't have any zeros because it's just e to the f. And so you only get the other part, and the other part is just Poisson representation. Okay. So maybe you saw this in another fashion. But let me just say it. A function is bounded type. You can show that if and only if, when you take the log of your function, this has a positive harmonic measurement in the upper half plane. These two conditions are equivalent. Often in books, that's the definition you see, especially those focus on analysis. Okay, those focus on entire function, etc. Sometimes use this definition I gave. Okay. Okay, now we can finally, yes. Okay, now we can state the main result. So let's try to state it, and let's try to give an idea of the proof. It's going to be a long statement. Okay. Yes. So what's the main theorem? That's the result I wanted to present. It was last year. It's close to Christmas. I guess nobody works at Christmas, but I do. It was December last year. There is a new version some days ago. There was some other things that I included. But okay, so let me use another color. So let mu A be a Fs pair. Okay, so let me reserve some space for recalling stuff. Again, what's a Fs pair? Is something that you always have this identity. And for every test function, so this is a Fs pair. For every test function, if you integrate Fourier transform against mu, it's equal to a summation of the function against some coefficients, a lambda. Okay? Poisson summation is this way. A bunch of those crystalline measures we saw in the first lecture, the quasicrystals, at least the one-dimensional ones, would be in this way. And so it's just a measure on one side and some singular measure, pure point on the right-hand side. And so this would be a general Fourier summation formula. Okay, as general as you can sort of think. And the theorem now that I'm going to present is going to classify them all. Okay, under a decay condition on mu. Okay, so let be an Fs pair. So assume two things. Assume that this is finite. And that this is finite. And this is for some c. First condition can be dropped if you assume that mu is greater or equal than 0. It would be implied by the second. Okay, it's exercise. Which is the case for these crystalline measures come from these things. Mu is always greater or equal than 0. Okay. Then 1. If you define f of z equals 1/2. Oh, I should say something. Be a Fs pair, and I'm going to assume here that mu is real, valued. Okay? Is that a real restriction? No, it's not, because if I give you two guys, if I give a pair which is an Fs pair, you can show that if you write mu equals mu1 minus I mu2, where both are real valued, and you write A as A1 minus I A2, where both A1 and A2 are antipodal, minus lambda equals the bar of lambda, then these guys are Fs pairs, and this is real. Okay, so if I'm going to classify mu A, I can just classify mu J AJ. Okay. Okay. So then 1, you define this guy like that. It is weird to summate over the reals. I do know that, but it is what it is. Okay, define this function, then this guy converges. Then f of z converges. And is holomorphic. Two, there is some C1 positive such that f of z plus I C1. So if you translate the function a little bit, it becomes almost periodic. Which just means it's almost periodic in a strip above starting from imaginary part of z equals C1. 3, the condition I have in the paper is different than this, but you can show that it's equivalent. There will be some C2 positive such that, well, this is almost periodic. So we have to translate it, but you can show that this E of f, I erased, is well defined if y is above C1. Okay. This is the same as to say that no, wait. Yes. Yes. There will be a C2 positive where this is finite. And this essentially comes from the condition on A, because you will show that the A's are essentially equal to this guy for lambda positive, and this guy will vanish for lambda negative. And a EF of 0, you're going to show that is, I don't know, A of 0 is the real part of this guy. So this essentially comes from the condition A. And 4 is E of f is bounded type. And the mean type of E of f is 0. Okay. Yes. Okay, and that condition is what I defined the exponential growth. Okay, in the previous class. Okay, so if you have a guy like that, mu real valued, so satisfy this identity for every. So the only condition you have is satisfy this identity for every test function and have these 2 decay conditions. The first you can drop if mu is positive. Then you have these 4 conditions. And then you have the converse. Conversely, if I give you f such that if conversely, given f from C plus to C holomorphic, such that 2, 3, and 4 holds, then there will be a measure mu, real valued. I erase such that star holds, and the star will be this guy. So I want to say that, well, any other FS pair has to be built from an F like this. So if I just give you any holomorphic function such that these 3 conditions hold, then there will be a measure which satisfies this. Well, directly from the proposition you can see, because I mean this condition is exactly this other one. And if I define A lambda to be antipodal, using the Fourier coefficients, which you have to show that they will exist because you have this. So this will be a well-defined by the formula I wrote as long as y is bigger than C1. So if you define for lambda positive and A0 as 2 times the real part of EF at 0. In particular, the imaginary part here doesn't matter. It's sort of a, yeah, this is the buffer. Let me continue here. So there will be a measure, and if I define A in such a way, then mu A is a FS pair. Okay? So this completely characterizes FS pairs. Essentially, with this condition, because as I mentioned, in most, I would say in all constructions, you assume that A decays like a polynomial. So if you divide, you would assume something like to the power 100 or 10, something like that. I'm assuming very, very mild. So this is, you can think of it as essentially not a condition. The only condition is this one. So this would essentially classify all FS pairs for which the measure integrates 1 over t squared. Okay? Which you can drop if it was positive. Okay. You can go back actually with something less rigorous than 3. The converse actually holds true. If you replace 3, you could replace, let me open a box here. You could replace 3 by, say, 3 star, where you only require what you really need, which is for this sum here to make sense. The only thing I need is that local sums are well defined because phi is compactly supported. Then you can actually go back only with that condition, which is for the converse, we can replace three by 3 star. Let's see, by condition 3 star, which is just the local sums are finite. Because those guys will be the coefficients of A anyway, so that's the only thing you really need. And yeah, you can actually do that. So there is sort of you could say there is it's like an epsilon gap, which is going without the exponential decay. I don't know if it's possible. I don't think so. I think there if coming from here, just from that identity, you won't be able to deduce that your functions are most periodic. So one thing you might do is there are other notions of a most periodicity that if you don't assume this, you only assume this, then you might get from F, which one of them is called Bezikovich most periodicity. So perhaps if you just assume that, you could still get that Bezikovich most periodic, and then perhaps you could still write a result. Okay, so that's one venue of investigation that you might think. Okay. Okay. So it's sort of a running out of time. I have two options. I either give an idea of the proof or I give examples and applications. Vote. Let's vote. No. Who prefers examples? Examples and applications rather than see the proof. And the proof? Who doesn't want to vote? Okay. But essentially the proof is what I gave in the last lecture, which is once you have, this would be the fundamental identity. I mean, regardless if you're trying to prove one direction or the other, you always have this identity. Okay? So what you have to do is to interpret this identity as one instance of this for those functions g, w, z that I wrote. I think that would be Fourier transform. Okay, and then you have to, from here, to get this. You have to sort of see that with those conditions, these two things are equivalent. Okay. And just to recall you, the function g I'm talking about here is, I think, e minus 2 pi I w bar x 1 of x negative plus e 2 pi I z x for x greater or equal to 0 divided by z minus w bar. And you can compute its Fourier transform, and its Fourier transform is going to be exactly this function here, like 1 over this. Okay? Okay, so let's see some applications. So one nice application, let me see the way I'm going to present this. So you can formulate a Hilbert space interpretation of FS pairs. And that's what I want to give now. And then I can talk about, now let me give the example. So there's a construction of Kurasov in Sarnak. I think it's from 2020. Okay. They will construct an FS pair of the following form. I'm going to give you a polynomial, Q, of x, which is a trig polynomial. Okay. I'm going to give you a trig polynomial. And I'm going to assume that such that Q has only real zeros. Okay, example. Particular, the 0, 0 will be alpha n, no, sorry, beta n plus alpha. It will be the beta n plus alpha, n is an integer. But generically, you could do something like that, as I show you. I think I showed this in the last class. You can take Q to be the determinant of U plus, and you take a diagonal matrix where you put I L1x dot 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 I Lnx. Say U is an n by n unitary matrix, and you add a diagonal matrix like that, where L1 to Ln are just real numbers, say of the same sign, say all positive. In particular, this guy only has real zeros and is a trig polynomial. Why? Because if I put here a complex variable, say, then all these numbers will have norm 1 or norm minus, norm in absolute value bigger than 1 or less than 1. In particular, the determinant won't be 0. Okay, that's one way of generating them. It's not the only way. There are a bunch of ways. They're not always written in this form. Okay. Then I define this measure here. Where the gammas here are the real zeros of this trig polynomial. In particular, and m is the multiplicity of the 0. And in particular, if I use this guy here, this sum would be over beta n plus alpha, or n are the integers. So this would be Poisson summation, because the multiplicity is 1. Okay? So this is one way of generalizing Poisson summation. Okay? So they show this measure is crystalline. So they show that this guy is some, there will be some coefficients here, and phi s. Let me see if I wrote this right. Yes. Where for some s contained in the reals and some coefficients complex, and S here is a locally finite set. So just a set of isolated points on the line. They might accumulate at infinity. They actually will, but locally, you only have a finite number of points. So any bounded interval contains a finite number of points. Okay? And so how can we recover that construction from ours? Okay? So there is just a particular case of this. Why? Well, first of all, the left-hand side is sum over the zeros of a trig polynomial. Trig polynomials are entire functions of order 1. So the zeros are square summable. In particular, you would have this. Okay? But what you can do is the following. So exercise, if q of x is a trig polynomial with only real zeros, and I'm using this measure here, which only looks at the zeros and multiplicities, I can assume that q is real on the real line. That is, it only has real values on the real line. Why? Because right Radha-Ma factorization, there will only be an exponential there, and you just remove that exponential without altering the zeros and the multiplicities. So I can assume that q is real on the real line. So what I do is I consider this function here, f of z equals I q prime over q. Okay? F is almost periodic. Remember, q only has real zeros. So in the upper half plane, this function here is well-defined, holomorphic. You can show it's almost periodic. Why? Because as I told you, for almost periodic analytic functions, if a function never vanishes, then 1 over the function is also almost periodic. So in particular, it's a product of two almost periodic. Okay? So you have it's almost periodic. You can compute what's the spectrum of f. So so f would be a sum like this. And the spectrum will be the points where this function here is supported. You can show it's locally finite. It's much better, actually. This is a trig polynomial. This is a trig polynomial. You can just expand this in power series. If the imaginary part of z is very high, you can just expand the whole thing in power series. And you can compute exactly what this guy is and what the support of these points are. Okay. But this is a generic feature. If you have two almost periodic functions, this is locally finite, and this is locally finite, the spectrum. You do the quotient, it implies that it's locally finite. Plus, I think you have to assume that the spectrum is bounded from below, I think. But that's always going to be the case here, because you do have the final condition. So it's almost periodic, it's locally finite, Okay, if it's locally finite, that implies yes, that implies this condition. Okay, because if it's locally finite, it's a finite sum. A well-defined coefficient, so it's always finite. Okay, so you do have 3 star, you do have second, so now you only need the final one. And how do you show the final one? Well, it's sort of a real part of f is positive in the upper half plane. Okay, so assume that this is true. I will show that it is. So when you do e to the power f, what is this? It's 1 over e to the power minus f. Okay. Well, but this function here is bounded. In particular, e to the f is a bounded function divided by a bounded function. So it's bounded type. Okay. And you have to compute the mean type. But then this is a quotient of 2 trig polynomials. If you compute the mean type, actually, you can show easily that the mean type of e to the f is 0. Okay. It's essentially you have to compute the real part of this. You have to compute this limit of the real part of I f of yi. Sorry, this divided by y. But I mean, without this, this limit would converge. And so if you divide by y, it goes to 0. Okay. And therefore, it follows from this result that you have this. Okay. Then you have to compute this guy. And as I said, if you want to compute this side, you just, if z is high enough, imaginary part is large enough, you can just expand this. I mean, this guy is q, and you isolate one guy, take the constant, there will be 1, and you write it as 1 plus some trig polynomial. That trig polynomial will vanish if the imaginary part is very large. Then you can expand in power series, and then you just multiply everything and see what shows up. It's a mess. It's a mess here. It's a mess in their result as well. Okay. Can I have 10 more minutes? 5? Yes. So let's. I don't want to exploit you. So let's give a Hilbert space interpretation of this thing. Okay, and then we finish. So I guess for the physicists, that might be a nice thing. They like Hilbert spaces. And it exactly fits the picture you want for these quasicrystals you see. You want the measure mu, so you want the FS pair mu A, such that mu is greater or equal than 0, because it represents the atomic structure, and so it's positive. And you want the support to be uniformly discrete, as 2 atoms cannot get too close. Okay, so that would be uniformly discrete. In particularly locally finite. Particularly is locally finite. Okay, and so that would be what I want to present. But for that, I need some definitions. Yes. And then we can finish. Okay, so a Hermite-Billah function is an entire function. Entire. So we call E a Hermite-Billah function or Hermite-Billah class if E is entire function such that for z in the upper half plane. So what's E star? E star here of z is E of z bar bar. Okay? That's E star. So this is essentially saying that if you look at the complex plane, if you look at point C here and you look at its conjugate, the function E here is larger in absolute value than it in here. Okay, that's what this is saying. Okay, and to a Hermite-Diller function, you can associate a Hilbert space. The Hilbert space is called a de Bruijn space. Okay, and they are very nice Hilbert spaces because they fit this theory very nicely. Yeah. So we say that H is a de Bruijn space. So H would be a Hilbert space with some norm induced by inner product, a Hermitian inner product. So we say that H is a de Bruijn space if H is a space of a vector space of entire functions. So the elements are entire functions with the following three properties. One, if f belongs to H and f of w equals 0, then f of z, z minus w bar divided by z minus w belongs to the space. So let me erase this. And has the same norm. Let me write it at G. And the norm of G equals the norm of F. Okay, so if you have a 0, you cut the 0, put the conjugate, you end up with a new function in the space with the same norm as the function before. That's condition 1. Condition 2 is that it's a reproducing kernel Hilbert space. If for every w in C, if you consider this functional, take a function in the space and just evaluate at the point, this is continuous. Okay? That property guarantees a reproducing kernel Hilbert space. There will be a kernel for which f of w equals the inner product of f with the kernel at w. Okay? Just by Ries's representation. And the final one is, that's not so important, which is, but we usually put that if f belongs to the space, then you do the star operation that I defined there. It also belongs to the space and has the same norm. Okay? That's the three conditions of the de Bruijn space. Okay? Then there is a very nice result of de Bruijn that says the following. Theorem, I think it's again from the 60s, which says the following. If H is a de Bruijn space, then there is a function E of Hermite-Diller class such that f belongs to H if and only if the sup in y in R of the integral of f of x plus iy divided by e of x plus I norm of y squared dx is finite. In that case, the norm of the space equals the sup. Equals this sup here. And moreover, the sup is attained at y equals 0. Okay? It's if and only if, which means that I'm also saying that if I give you any Hermite-Piller function and I define the norm and define the functions in the space as being entire functions such that this is finite, you can show that the sup is attained at the real line, and that thing defines the norm. That norm induces a Hilbert space which has these three properties. Okay? It's complete characterization. Okay? So what's the Hilbert space interpretation of what I want to present? Yes, what is this thing? 16, oh, 15. Yes, please. Oh, yes. And then we finish here. So theorem. Let me roll this guy here. So the question is sort of a, well, I asked that question. Maybe it's not natural to you. Is that can we include the extra condition such that in a way the Hilbert space itself will sort of expel, sort of produce Fs pair. And such condition exists. So let H with some norm be a de Bruijn space. Oh, by the way, when we have this, we write that H equals H of E, where H of E is the space constructed with this norm, right, and that condition. De Bruijn space. So it will satisfy these three conditions. Assume also, oh, I have to write something. So remember I told you that the third condition here, the second condition, implies the existence of a kernel. That implies that f of w is the inner product of the space, the inner product that induces the norm. There will be some kernel, k, w, z, such that for every w, as a function of z, k belongs to the space, and if you take in a product, it gives back the value of the function. Okay? So the condition that I'm going to write depends on the kernel, but the kernel is uniquely defined in the space. Okay, I didn't say, but the function that gives this representation is not unique actually. There is a one parameter family of things that can do this. Okay, it's, you think of like applying a Mobius transformation, something like that. H4, assume there is some alpha in the upper half plane such that that might look weird, but it is what it is. This is minus, and this is plus. Suppose that such a function is almost periodic. Okay? Then the space produces an FS pair. Yes, but I want this at the same time. Then there is a function E over mid-pillar class. I'm not going to write, say E is a mid-pillar class, such that H equals H of E. Okay. And if I write E equals A minus IB, where A and B are real on the real line. So usually we call this a real entire. So A would be E plus E star over 2, and then B would be E star minus E divided by 2I. So they're real on the real line. So if I write it like this, and if I define mu equals 2 pi, the sum of the zeros of a function b, with the residues of a over b at z equals gamma and delta of gamma, and I define a lambda equals a minus lambda bar equals E of I a over b. There is H and B such a, and if we write it like this, I forgot to say, then I a over b equals star, where star is this function here. Therefore is the most periodic, so I can take this guy, and this guy here is like that, and again a of 0 is 2 times the real part of this thing. Then if there is such E, if we write it E as A minus IB, then we have this thing, and if we let mu like this and A like this, then mu A is a FS pair. Mu is greater or equal than 0. Support of mu is locally finite. That's it. Conversely, if mu A is a FS pair, mu greater or equal than 0, and support of mu, I think I have to ask something more. I have to ask that this is locally summable. I mean, the only condition really that you need. So if S are pairs with positive support is locally finite, and as the main result, I think we have to assume that A has exponential growth. And A has exponential growth. Then mu A comes from this. Okay. Which is it's nice for the case which is greater or equal than 0. That's the case that this is one-dimensional, of course. There's the question of going to higher dimensions, but at least for 1D quasicrystals, you have a Hilbert space interpretation. Okay. It was, just as a side comment, it was sort of also I was lucky that this was the stuff that I studied in my PhD thesis. So I sort of saw the connection, but still the result was sort of surprising to me as well, because I never knew that these two worlds could be connected somehow, but they are, for some reason. Okay. And we can stop here. Okay. Thank you. Questions, maybe? Yeah. Any questions? Okay, then you can thank me again. Yes.